Hello YouTube. For today's lecture, we'll be talking about the real numbers, and we're going to be deriving them axiomatically, and then we're going to start figuring out how we can derive them by construction. So the real numbers are something that are very important in real analysis, and they can basically be summarized by these four axioms. There exists some set n that is not bounded above an r, and n are the natural numbers. That's 1, 2, 3, and in succession. So number 2 states that there exists some n, little n, in big N, the natural numbers, such that 1 over n is going to be less than an epsilon. And epsilon, if you're not aware, is just some very, very teeny tiny number. So when mathematicians talk about an epsilon, they're generally saying we want some number to go to a very, very small value, which is used a lot when we're talking about limits and so on and so forth. So 3 is if S is bounded above an R, that is, if there is a set S that is bounded above an R, and U is in it, if U is its least upper bound, then for any epsilon greater than 0, and remember epsilon means any teeny tiny number, there is an S, little s, an S, where the upper bound minus epsilon is less than the upper bound. So there is always some number less than our upper bound. So our fourth statement states, if there is some x, y that exists in R, which is our real field, then there is a q in the rational numbers that exists between those 2 points. So notice that none of these properties is part of the definition of a complete ordered field. And we know that the real numbers should be, at least theoretically, a complete ordered field. For instance, just because n is not bounded above in Q does not guarantee that there is no real number bigger than every natural number, right? So, and just because no rational number bigger than 0 is smaller than every 1 over n, it does not guarantee that there is no positive real number smaller than every 1 over n. There must be something about least upper bounds that is used in a useful way to prove these results. So let's establish that. Okay, so to establish one, suppose n is indeed bounded above, so there exists some u in n, right, where u is a least upper bound. So since u minus 1 exists and is smaller than u, that forces u minus 1 to not be an upper bound for n. This is just basic manipulation of the definition. Right. So, of course, that means there must be a natural number n, right, that is less than this, that is greater than u minus 1. But then that would give us the contradiction that there exists some natural number plus 1 that is greater than our upper bound, right? So that means by definition that this cannot be an upper bound because there is an upper bound, there is a number that is greater than it, which contradicts the definition of a least upper bound. So that means that u is not an upper bound for the natural numbers, and that's a contradiction. And then that gives us the statement that n is not bounded above in R. So that qualifies our first statement. So our second statement, a little bit of lag there. Our second statement says, for the second one, note that by number 1 over epsilon, which is again the teeny tiny number, is not an upper bound for n. So that means that there is an n, a little n, that exists in N with 1 over epsilon less than N, right? It follows directly from the field axioms that just by manipulating this using the basic multiplication and division that we know of from the field axioms, that 1 over N is less than some epsilon. Okay, so that kind of gives us a sense for why number 2 is true. Okay, for number 3, if S were bounded above, we know that it does indeed have a least upper bound U. So if there is no S in little s, so if there does not exist a little s in big S greater than least upper bound minus epsilon, then U minus epsilon must be a upper bound, which we know this isn't true, and that would produce an upper bound which is smaller than U, which is a contradiction, giving us that there must exist. By contradiction, we assume that there must be some U minus epsilon that is less than S, but is greater than or equal to some upper bound, or less than or equal to some upper bound. Okay, so for 4, if x is less than 0 and is less than y, we could just choose q equals 0. A little bit of lag there. Q equals 0. Otherwise, we can assume that 0 is less than or equal to x is less than y. So otherwise, it would be something that looked like this. Part 2 implies that we can find some 1 over n in Q with 0 less than 1 over n less than y. So S is equal to some Q that exists in Q such that 0 is less than Q is less than y. With this definition, the least upper bound must equal U, and clearly U is less than y. So we cannot have a U less than y, since if we did, then by our second proposition, we can find some other 1 over k less than y minus u, and by 3 we can pick some q in u, some q that exists in q, so some rational number, such that u minus 1 over k is less than q is less than or equal to u. We would then have a situation where we have q plus 1 over k less than or equal to u plus 1 over k is less than or equal to y, which would put the q plus 1 over k, which is clearly rational, in S, contradicting u being our upper bound for S. So that means our least upper bound in S must equal u, and by our second proposition, we assume that we prove that we can find a q in S such that such that y minus q is less than y minus x, i.e. x is less than q is less than y. It's a funky looking q there. But that should that validates the fourth axiom, and why that validates our real numbers. The immediate consequence of this result, already seen in this proof, is that if R is a complete ordered field and R is any element in it, then R is equal to the least upper bound of Q in Q such that Q is less than R. Thus, the elements of a complete ordered field are closely connected with the rational numbers less than them. An actual construction of the real numbers uses this very close connection, and we'll see this in the coming construction. But before we consider such a construction, let us deduce one more consequence of the axioms in an ordered field. So we can consider a more general roots and talk about roots that are square roots of any positive number rather than just the number 2. So the Roots Theorem states, so we want to talk about roots basically. So let's talk about the Roots Theorem. Okay. Let R be a complete, a little bit of lag there, ordered field, okay, and let A greater than 0 be a fixed element of R. Now let n greater than 2, greater than or equal to 2, be a fixed a little lag natural number, then exists a unique R in R such that Rn is equal to A. So let's go about the proof for what this is actually arguing. So if we let S equal Q in the rational numbers such that Q greater than or equal to 0 and Q to the n is less than some A, then S is non-empty since 0 is in S and S is bounded above, for instance by 1 if A is greater than 1, then and by A if A is less than 1, and then by A if A is greater than 1. This last statement can be verified just by using the field axioms. So S has a least upper bound, which we will call R. So there exists a S has a lub, least upper bound. We'll call it R, equal R. And we'll try to show that R has a desired property, Rn equals A. So, true. Is this true? The uniqueness follows from the field properties. It does not have to do anything with the particulars of how we construct R, and you can verify that for yourself if you want. First, we show that we cannot have Rn less than A. The strategy is to show that in this case, we'll find a rational Q larger than R, which satisfies Qn is less than A. So we want to first show that cannot have Rn less than A, and we're going to show this by Qn. We can find a rational Q larger than R, so this Q is larger than R, less than A, which will contradict R being an upper bound for S. To that end, we consider for small epsilon greater than 0. So, for instance, we can restrict our attention to epsilon less than 1 and R plus epsilon to the nth power. So the additional terms involve higher powers of epsilon and lower powers of R, and constants determined by n. Since we know that R is bounded above by a larger A and 1 depending on A, it easily follows that there is a constant m depending only on a fixed A and n, such that if we consider some R plus epsilon, let me make that straighter. So if we consider some R plus epsilon to the n equal to Rn plus n to the epsilon R n minus 1 plus some additional terms, right? We don't need to worry about those. We know that it is bounded above by a larger A and 1. It easily follows that it exists some constant m depending only on the fixed A and n, such that R plus epsilon to the n is equal to Rn plus n epsilon Rn minus 1 plus epsilon squared. And this is going to be, let's just say this is less than some R to the n plus m epsilon, where m is just some constant. So m is just some constant. If Rn is less than A, we can choose epsilon to be so small that the constant times epsilon is less than A minus Rn. So we can choose some epsilon m epsilon, where remember m is just some constant, that is less than A minus Rn. Which means that R plus epsilon to the n is less than A. Now we know from the earlier result that there is a rational Q with R less than Q is less than R plus epsilon, meaning that there exists some rational number between R and a number slightly larger than R, slightly larger by epsilon. And from the algebraic properties, Q to the n, so we know this is true. So I'll just put this so I have more room. So we know this is true from the axioms from before, And from the algebraic properties, we can extrapolate that there exists some Qn less than or equal to r plus epsilon to the n is less than a. So Q is in S, contradicting R being an upper bound for S, meaning that the statement Rn less than A is not true. And remember to prove that Rn is equal to A, what we're essentially doing is we're first doing this, and then we're going to go forward and prove that Rn is not greater than, it's not less than A. And if both of these are not true, then by the ordering principles, that would have to mean that Rn is equal to A. So what we're kind of doing in this proof is sandwiching our result, sort of. Similarly, so we'll show that Rn cannot be greater than A by showing that in this case we'll find some epsilon which is smaller than R, but which still satisfies Qn less than R minus epsilon for every Q in S, which would contradict R being the least upper bound for S, therefore giving us our contradiction. As we did before, R minus epsilon to the n is equal to R to the n minus some constant n e to the r n minus 1 plus e squared and some simultaneous additional term. So these are additional terms, and I'm just gonna say they're additional, and I don't have to specify them because epsilon is considered to be such a small number. We're constructing an epsilon to be such a small number that just these alone are insignificantly small and won't give us any troubles in our problem. So it'll still equate to an equality. The different additional terms are bounded below by C for some constant. For C is some constant depending on a fixed A and N. So what that means is from this I'm assuming there exists some R minus epsilon over N to the nth power, which is greater, a little bit of lag there, which is greater than or equal to Rn minus n epsilon r to the n minus 1 minus epsilon squared c, which is the equivalent of r to the n minus epsilon 2 to the n r n minus 1 minus epsilon c. So that's just by algebra. I'm just taking out the epsilon there. And by choosing an epsilon so small that this term here is equal to k, right? This thingy is equal to k. We have some r minus epsilon, r minus epsilon. Let me write that a bit neater. We have some r minus epsilon to the n that is greater than, right, this part that is greater than r to the n minus k epsilon. So if we're turning this conglomerate into that goes to some constant k, because we know this is a constant. We're saying that constant times epsilon gives us this expression, and that's always going to be less than r minus epsilon to the nth power. So what that tells us is that if r to the nth power is greater than a, we can choose some epsilon to be so small that, so if r to the n is greater than a, right? We're proving our contradiction. Then we can choose some epsilon so small that k to the epsilon is less than r n minus a, which means that r minus epsilon to the n is greater than a. Thus, r minus epsilon would be an upper bound for S, contradicting R as the least upper bound. So this contradicts that Rn that Rn, this lag is killing me. This Rn, okay, that Rn over is greater than A is a true statement. So this contradicts that and proves that by trichotomy, now we've proved that if Rn is not greater than A, nor Rn is less than A, that must mean that Rn is equal to A. This proves our theorem, and this is the result we want. Okay. Now we're ready to provide a construction of real numbers. We've already briefly talked about the axioms, and now we want to actually create the real numbers. Notice that we've considered in our general complete ordered field R several constructions of sets S of rational numbers, and we applied the real numbers to them as well, which are bounded above, and in which we use the least upper bound of the set to consider the element of R which we were interested in. We take this approach for a construction of R. It is the approach used by Dedekind, and the sets of rational numbers we use are called Dedekind Cuts, named after the mathematician. This construction of R makes it very easy to show that every complete ordered field R is the same. And this idea is crucial. This is that every complete ordered field R is the same as big R, the real numbers. I.e., there is a bijection from the constructed R that we created by axioms. So the R defined by axioms, it bijects into what we consider the real numbers, right? Because this is just a set that we define, an ordered field that we defined. But to construct something, this gives us a slightly different I guess, definition you could call it. But the point is that this is always the same as the big R, which preserves addition, multiplication, and the order on the respective set, on the respective fields, not sets. This construction also makes it easy to show that the least upper bound property is satisfied, and it just follows from set inclusion. The pain is in verifying the algebraic properties, addition, multiplication, those sorts of things. But the construction of additive and multiplicative inverses requires a lot of effort, and the verification of the ordered field axioms is a bit of a really tedious slog. So to do this, it takes a lot of work. So we're gonna engage in the details next time, but here's the easy part. We defined a Dedekind cut, so Dedekind cut A to be the proper subset. It is proper subset of the rationals with following properties. Okay, so the cut alpha is non-empty, i.e. if Q, if Q is in alpha, then P is also in. And if Q is in alpha and P is less than Q, then P exists in alpha. Another point, if Q is in alpha, there is a P in alpha with P greater than Q. So exists some P in alpha such that P is greater than Q. And obviously this is a different P than the one in this statement. Another property is if we visualize the rational number line in the usual fashion, then a cut is an open ray extending to the left. So let's just assume that this is, let's make this a number line. Then when we say a cut, like if this is the real number line, then a cut is just some open ray. So open meaning that it's not there's a hole here, right? And it goes to the right or to the left. It is non-empty, so everything to the left of any point, or in this, anything to the right of the point in this case is also in it, and there is something in it to the left of it. For example, if R is any fixed rational number, Q and R, Q and some fixed rational number where Q exists in Q such that Q is less than R, this would be the definition of a cut. So while this, the equivalent statement, where if I put equal to sign, this is not a cut because we want an open cut. A closed ray is not what we consider a cut. An open ray, where we have the set greater than Q but not including Q, is what we consider a Dedekind cut a Dedekind cut R. So if this is cut R, that is how we define that. And if A is any fixed positive rational number, then by the Roots Theorem, we know that for Q in the rationals, there exists some Q less than 0 or Q greater than or equal to 0 where Q to the n is less than some A. And this is also considered a cut, where we have some value of Q that is cut to be greater than A. Or in this case, to be greater than A, because we are less than in this case. So the easy definition of the order, if alpha and beta are cuts, we define alpha less than beta to mean as subsets of Q, A is contained in B. So if this is less than this, that means that there exists some alpha contained in beta. So if this goes on to infinity, this continues to infinity. So this set is entirely contained in this set. It's easy to show that containment as defined here satisfies the trichotomy on cuts, meaning that alpha can be greater than beta or alpha can equal beta, and of course it's transitive. It does not satisfy the trichotomy of all subsets of the rationals, but it does for this collection of Dedekind cuts. Moreover, containment easily yields least upper bounds. So that means if S is a collection of cuts which is bounded above, that means meaning that S is non-empty and there's a cut beta such that alpha is less than or equal to beta for every alpha in S, then let gamma be the union of all the subsets of Q that are in S, and it's easy to show that gamma itself is a cut, even though it is a union of all the subsets, and it is a least upper bound of our set S. And we're going to go more into this statement next time, specifically talking about the least upper bound properties with the Dedekind cuts. So stay tuned for our next episode, and while you're here, don't forget to leave me a like, and please subscribe for more content in the future.